This is one of the most interesting sessions of this conference. And the thing is that to do here is look at the pictures, enjoy the pictures, because the developments are unbelievable. We will have 3 lectures, and the first one by Knut Urban of Germany. I met him 32 years ago in Les Ouches in France, and we are friends ever since. He has visited Israel multiple times, gave talks here, and he's the man of the world. He and his colleagues overcame the problem of spherical aberrations in electron microscopy. This was a major, major obstacle. While spherical aberrations were corrected in optics many, many years ago, no problem. In electron microscopy, this was an obstacle. So I'm calling Professor Urban to the stage to tell us about his development, his very important development, and the consequences, and what you can do today looking at crystals in the electron microscope. Please, Knut.
Thank you very much for the introduction. I would like to start my talk by expressing my sincere gratitude to the Israeli Academy, and in particular to Danny Shechtman and Raphael Levine. I would like to express my particular gratefulness for being able to come here to the 70th anniversary of the State of Israel and to express my sympathy, my friendship to my long friends here in Israel. So the last 4 days have shown that in our views of the world, atomic molecule concepts play an important role. That means we talk about atomistic phenomena, molecular phenomena, but nevertheless, most of our experiments are carried out with ensembles of atoms and molecules, and then it's by interpretation that we conclude on the properties of individual atoms or molecules. So this approach works perfectly over a long, long time, but there are cases where this ensemble averaging does not work very well, and this is the time of microscopies. In microscopies, we just limit physical and chemical space to a single entity. And then, provided that we have enough signal, we then try to get directly the properties or the behavior of individual atoms or molecules. And I have had the privilege to watch, or even more, to be a protagonist of the development of aberration-corrected electron optics, and this is what I'm going to talk about, because aberration-corrected electron optics, aberration-corrected electron optics have allowed then in turn to develop atomic resolution transmission electron microscopy. So this will be mainly about dead matter, but nevertheless you can see some nice images, and I really admire the talks which I have heard here on living matter. So I would like to start with a brief technical introduction, and I start this by saying that the performance of optical devices is necessarily always limited by aberrations. So when we talk about an imaging process in an optical system, we ideally have a situation like this. We have an object space point, and with this point we just have a we have ideally a collinear transformation from the object space into the image space. In reality, things look much different. We have aberrations in the lenses, and this leads to a highly nonlinear transformation, which means that we have a highly distorted image of our point P here. So if we would represent an ideal lens by a situation like this, independent of the angle these individual imaging rays are making with the optical axis, we get the same action to all these beams. And this is the reality. That means the lens shows all kinds of phase changes, of distortions of the image, and these optical operations are sorted here according to the powers of angle the individual rays are making with the optical axis. And now let us concentrate for brevity on one of the aberrations, and this is spherical aberration. Spherical aberration means that the refraction power of the lens is much stronger at the periphery than in the center of the lens. And this leads to the fact that we have the focal length not to be constant. It's longest along the optical axis, and then it decreases, which means that this point P here is projected into an aberration disk rather than a sharp point. So the usual way to cure this problem is to introduce an aperture in the back focal plane of the lens, and this keeps these high-angle beams from contributing to the image. So you get formally you get an improved image, but you pay a dear price for that, because the laws of diffraction tell us that the information on the finest details of your sample, they are in these high-angle beams. So if you just keep them away from contributing to the image, you, of course, diminish the resolution. So in light optics, this dilemma was solved by Ernst Abbe in a very famous paper in 1879, where he showed that the spherical aberration of this converging lens can be compensated for by combining it with a diverging lens, and then you see the focal length becomes the same independent of the ray angle, and this started the triumphant progress of light optics, where today even the most simplest systems are consisting of a number of lenses which mutually compensate their aberration. So what holds for light optics in principle should also hold for electron optics. That means we have to have a diverging lens. So in electron optics, the lens action is performed by concentric magnetic fields, and this is where the problems start. Magnetic fields have to obey a basic law of nature, and this is the Gauss Law of Magnetism, which is one of the four Maxwell's equations. And this Gauss Law of Magnetism says that the divergence of the magnetic field vector has to be zero, which means in practical terms that the magnetic field lines have to be closed, and as a consequence of this, you only can construct converging but no diverging lenses. So to overcome a basic law of nature, of course, is a formidable task, and therefore even 60 years after the invention of the transmission electron microscope by Ernst Ruska in 1931, in 1991 we still had no chance to correct the aberrations of in electron optics, and this means that electron microscopy also failed to reach atomic resolution, which was urgently needed for these upcoming nanoscience developments. So I refer to the year 1991, and this was the year when the Volkswagen Foundation granted a project for us in 1991. Us means Max Heider, Harald Rose, and myself. And there we claimed that we could overcome Gauss' law by employing multipole lenses. So many people laughed at that time on this concept because multipole lenses a priori are introducing terrible distortions of your electron wave field, and this meant that you were just replacing one evil with another. That the situation is better can be shown by this short sketch. Here we have a 6-pole, plus and minus mean north and south. It's a magnetic 6-pole. And now we send a parallel electron beam into this 6-pole, and as expected, this is distorted into a triangular shape. So when you have an optically thick 6-pole, then you can show that this triangular distortion can be decomposed into two parts which are independent of each other. And the first one is a symmetric spreading of the beam, and the second is this triangular distortion. Now the trick is to use two hexapoles and of inverted polarity, and this eliminates this triangular distortion, and you get what you are looking for, the diverging lens. So this looks simple. In reality, it's quite complicated and difficult, last not least, because you still keep these operations, and everything you do just has an action on all these operations. So it took us 6 years till 1997 when we could submit our paper to Nature, in which we could show that we had constructed the world's first aberration-corrected electron microscope, and that we were able to show a resolution of this microscope with this correcting system here of 1.2 angstrom, which was by far better than any resolution that had been achieved at that time at 200 kV. And with this record resolution, we were able then to image and separate these gallium, these dumbbell atoms consisting of gallium and arsenic, to separate these dumbbell atoms which have a separation of 1.4 angstrom. And this, in a sense, started the atomic resolution electron microscopy we are used today. So our instrument has become, so to say, the mother of an entirely new generation of microscopes which rely on aberration correction. We have an estimated number between 650 and 700 instruments installed worldwide, and with an exception of 2 or 3 handful, these are the Nion instruments, all these instruments rely on our double hexapole corrector principle, independent on whether these are TEMs or STEMs. So many of you may not be familiar with the nomenclature in electron microscopy, so let us briefly talk on these acronyms. With TEM, we mean the conventional transmission electron microscope, incoming beam, lens system, intermediate lenses, and down here we have the image plane, and there the image is recorded by a CCD or a CMOS camera. And this was invented in 1931 by Ernst Ruska. With STEM, we mean the scanning transmission electron microscope, which was invented by Manfred von Ardenne only a few kilometers away from Ernst Ruska at that time in 1937. And here we have the incoming beam, we have the lenses, and these lenses are forming a very fine resolution limiting beam, which is then scanned over the specimen, and the transmitted electrons are caught, are registered by a detector down here, and the signal is used to obtain the image. So most of the people ask me immediately about the resolution of these new technology, and they mean the Rayleigh resolution. That means we have two atomic contrasts, and we move them together until we just cannot distinguish them as separate, and this resolution is nowadays about 50 picometers or better. The The record was recently set by a STEM microscope at 300 keV, where they could resolve 40 picometer atom pairs in gallium nitride. So that's the optimum that can be done with respect to resolution. But as soon as you have your atomic contrast separated, what counts is no longer resolution. It's precision. That means you have two atomic maxima, and you now measure, for instance, the separation between these two, well separated. Then what counts is not the resolution, but the precision with which you can measure the maximum in these atomic contrasts. And this precision is an extraordinary number. It's 1 picometer. That means we can measure shifts of atoms in the order of a picometer. And this is an extraordinary number, last not least, because 1 picometer is just 1/100th of the Bohr diameter of the smallest of all atoms, the hydrogen atom. So that marks the state of the art today. And the question is, of course, what we can do with this. And first of all, we want to see nice images, because, as you said, that's the pleasure in this talk. You see images. And so we should say that we do single atom column imaging. In most cases, we have a situation like this, and we look at these atomic columns end on, and this leads then to the image. That means behind these particular points, there are other atoms in most cases. So I start with showing you Z equal to 1, nuclear charge equal to 1. That's hydrogen. So you see here that the atoms appear dark on bright background. So this weak contrast here is the contrast of hydrogen in yttrium hydride. Z equal to 3, lithium, very important element today. So you see the individual lithium atoms here in this lithium, cobalt, oxygen. Z equal to 5, boron, this is boron nitride, and you see now the atoms bright on dark background besides the nitrogen here. Z equal to 6, carbon, this is graphene. We have a single layer graphene, double layer graphene. Very nice today what we can do there. Z equal to 7, nitrogen, we have already seen that. And now oxygen, Z equal to 8. And we see oxygen quite nicely here in between the titanium atoms, and we also see the strontium. So when we published our work on oxygen in Science many years ago, this was considered a sensation, because before that, oxygen could never be seen directly in electron microscopic image. So that means before the advent of aberration correction, oxygen could not be studied. Microscopy was blind with respect to this important element. Of course, we can do much more. We can now measure these atomic structures. We can determine the atomic species. We can measure atom concentrations, measure electronic states, measure magnetic fields, electric fields. We see in a few minutes, we see an example of phononic states which we can measure, and we can carry out experiments in the electron microscope, just to give you an overview of what is done today in these instruments. And we use for this, we use quantitative intensity measurements, not only images, we measure the intensities. We do quantitative field spectroscopy, X-ray spectroscopy, holography, special contrast techniques for measuring electric fields, and also magnetic fields. So this tells you that, and I will show you some examples as long as the Chairman allows me to speak. Modern electron microscopy is more than images, it's measurements. We measure positions, we measure intensities, we can do picometer precision, and for this we have, because we are in quantum physical dimensions, we have to simulate the image process by solving the Schrödinger equation and by solving for the optical paths. We will see that. So this gives us access to the picometer space where much of physics and chemistry happens in solid state. And there we have this wonderful technique of DFT calculations. So some of the work today is combined, it's done in tandem, high resolution and DFT calculations to better understand the results. So now examples, and the important point in all these examples is I'm not discussing these examples down to any physical or chemical detail. I only want to show you in a comprehensible way what electron microscopy in atomic dimensions can do. That's all you should take home, not the details. So I start with something which is very modern today, research on lithium-ion batteries. So a lithium-ion battery has essentially three parts. We have a lithium-containing compound, we have a solid-state electrolyte, and then we have graphite, which accommodates the lithium atoms in the chelation compound. So upon charging, the lithium flows into the graphite intercalation configuration, and upon discharging, the lithium flows back into this, and this is accompanied by a discharging electron current through the outer circuit. So this lithiation and delithiation process can be nicely seen in the electron microscopic images. So this is an ideal case, lithium iron phosphide. This is delithiated, and we see in the position where the lithium atoms should be, atoms dark on bright background now, there's nothing. Lithium is out of this compound. Now we discharge again, and we now see these lithium atoms here in between the other atoms of this compound. So this is an ideal example, but more interesting is this one. This is a study on lithium, titanium, oxygen, spinel as a lithium-containing compound. This is real research work, while the other things were nice images. And here the contrast is quite ambitious. So we see here the two lithium atoms of this lithium-4 titanium compound. Here is weak contrast here at the tip of these arrows, and we get two intensity maxima there. So when we now put lithium back by discharging the battery, we are forming a lithium-rich compound, lithium-7 from this lithium-4. We add 3 lithium atoms here, and this gives only a single atomic maximum, which I have indicated here. So that's the position of the lithium atoms. But we can do much more. This microscope is also a spectrometer. That means we can now try to find out where the electrons are going when they are flowing here into the lithium-containing compound. And the average valency of titanium is 3.4 plus. So where are the electrons in reality? And for this, we take EELS spectra, which give us a fingerprint for titanium 4 plus and titanium 3 plus. And it turns out that all these electrons, these three extra lithiums, they go into this particular titanium position, not in this one. Because the electron states here, because of the special environment, they are able to accommodate this. So we have titanium 3 plus here. So you see, we not only do structural investigation, we also can contribute information for the electronic state. Since this is a chemical symposium, I tried to find at least one more example of chemistry, and I came across this one, the catalytic sites for dehydrogenation of ethane into ethylene. And this is normally done with the steam cracking process, high temperature, high pressures, but it's done in large quantities in industry. So since a few years, people are trying to have much more mild conditions by using a catalyst, and this catalyst has been widely studied, molybdenum, vanadium, niobium, and tellurium. It's called the M1 compound. So, as always, people are asking questions about catalytically active sites, and here you see the long crystals of this, and there is agreement that the catalytic site should be, in any case, on these faces, these 001 crystal faces of these long crystallites. So the arrows here are pointing, are indicating the sides, the side facets of these crystals, and we are now studying these with the next image. And it's also quite well accepted now that the tellurium S2, S4, S7 clusters, which are tellurium together with vanadium and molybdenum, that these are the places where the catalytic reaction takes place. So we cannot help here very much, but at least some things we can do. We can take images like this. So this is a cross-sectional image of this crystallite, and we see it, all the atoms are visible. But superficially regarded, the contrast is dominated by this five-fold niobium and molybdenum octahedra. And what we can do in this microscopy is, in particular, we can study these facets here. And you see that we have a large fraction of these facets have the orientation 0, 1, 0, but there are also 1, 2, 0 and 2, 1, 0 facets. So the atomistic study goes like this. We have here the 0, 1, 0 facet, and it turns out that the surface here, atomistically regarded directly in the microscope, it's passivated against this catalysis because these five-fold units form a contiguous coverage of this plane. That means this is not very helpful. But the situation is different in these 1 to 0 facets. Here we have exposed directly these S2, S4, S7 tellurium arrangement to the outside. That means catalytic reaction is going on in these facets. That means these arrows here, these are areas where we have a very intensive catalytic activity. So this takes place here as well, but nevertheless, they are forming mainly the catalytically active site. So that's the type of information you can get from electron microscopy. Next one is example is how electron microscopy can contribute to electronic device design. And here we talk about capacitors as sandwiches of lead siliconate titanate sandwiched between two strontium ruthenate electrodes. And the width here is about 10 nanometers. And now we magnify, and here we see now the atomic structure of this interface here. This is the lead siliconate titanate. This is the strontium ruthenate, the metallic part. And then we magnify further. We go to the right here, and we see immediately the material is polarized. It's a ferroelectric which is polarized. And we see it in the atomistic image directly because we see that this oxygen atom has moved out of this zirconium-titanium atom row. And the consequence of this is a ferroelectric moment on the unit cell level. That's the unit cell. Yeah? And we can measure this oxygen atom. These are the neighboring titanium and zirconium atoms. And we see that it has shifted by 23 picometers. Very little, but there is the function, this shift of the oxygen atom. So what is interesting is that we have this 23 picometer shift, but when we go down to the interface, we see that this shift decreases. And this has an effect on the permittivity of this layer system, and we can measure this now. We have here the lattice constant of ruthenate and the lattice constant of the siliconate titanate, and we see that it's not abruptly changing. It's changing in steps of about 5, 7, 8 picometers, and we can measure this. Now here we have the shift of the oxygen atoms out of the zirconium-titanium atom row, And we see also this goes continuous from 8 to 16 to 20 to 23 picometers. So the next example is a sketch of the steps which allow you to do genuine picometer microscopy. It's not easy to do this, but the steps can be defined, and then you can understand how we are doing that. It's very ambitious to do picometer microscopy. So our example is a single layer of lanthanum aluminate sandwiched between two strontium titanate layers by pulsed laser deposition. So I'm interested to see whether the atoms just take their genuine positions, or whether there is intermixing going on. So we do a quantitative study, and of course we start with images. So this is one of the images, and we see all the atoms. And we measure now pixel by pixel. The pixels are very small. We measure pixel by pixel the intensity, which gives us a large amount of data, and they present the primary data set. Unfortunately, this primary data set cannot be taken as it is. And you can immediately see this by your eye. You just look at lanthanum 57. It shows a relatively weak contrast here. The contrast is weaker than the contrast of oxygen here. In spite of the fact that oxygen is only nuclear charge 8, it has a much weaker scattering power. Nevertheless, it's much stronger. And this is a result of dynamic electron scattering, or if you wish, it's Bloch state, Bloch wave propagation in the crystal, which of course has to be compensated for, because we want to do quantitative intensity measurements. So we have to correct for. These are the individual steps. Each is taking quite some time to go into detail, but that's not what we want to do here. Of course, the first thing is to look whether our CCD camera data are correct. That means we have to look whether the camera really transfers all the individual Fourier components of our image correctly. So what is the modulation transfer function? You just take your microscopic image, then you Fourier transform it, and send all individual Fourier components to your 360 camera. Then you look what comes out, Fourier transform back, and synthesize the output image. And of course, you hope that this image and this image is the same. And it's not. So if this is the wave vector of the Fourier components, fine details are here, crude details are here. So ideally, it should look like this. All Fourier components equally well transferred. The reality is like this. That means the contrast decreases, becomes bad, it's damped when you go to the high frequency components, and these are exactly those which you want to see, because they contain the information on the finest details. So this, of course, has to be taken into account. We have to correct our data with respect to the camera modulation transfer function. Then there is unfortunately also electron absorption going on in the microscope. I don't go into details with that, but I want to give you just an impression of a very interesting effect, which was only discovered a few years ago. And this is the effect of Johnson quantum noise on the images. And this most probably is the end of microscopies. We can improve the optical qualities, but this is an intrinsic limit which we reach in high resolution. Johnson quantum noise. What is the background of this? So in every microscope, you have metal parts. So the electrons are just going very close to metal, pole pieces, vacuum liners, and so on. And in these metals, you have mobile electrons. Mobile electrons mean currents, and according to the Maxwell's equations, each current means a magnetic field. So the electrons just going, for instance, to this liner, it's 10 centimeters long, And at 230,000 kilometers per second, these are highly relativistic electrons, this takes about 500 picoseconds. During these 500 picoseconds, you have enormous amounts of random currents of the metal electrons and their nanomagnetic fields. And these 500 picoseconds are too short to average this out, as people have thought until a few years ago. That means each electron, by the way, there is only one electron in the microscope at a given time. But they are so fast and they just, so each electron just sees a snapshot of the sum of all these nanomagnetic fields, and when you just send in the electrons, they just arrive in the image at slightly displaced position, and this broadens the atomic contrast, which of course when we want to be quantitative we have to take into account. Another point now, dynamic electron diffraction. You have seen the example of lanthanum compared to oxygen, and the background of this is relatively easy to comprehend. When you send in an electron wave onto a crystal, the negative electrons get attracted to the positive atomic strings, and they perform a oscillatory motion around these atomic strings. And down here, what comes out of the sample depends on the thickness, and it depends on the nuclear charge. So we get an effect of this Bloch wave channeling through the crystal on the image, and this has to be calculated solving the Schrödinger equation, and I don't want to go into details with this. So there are other corrections which have to be done. We are in the picometer range. So even when you have a sample which is about 10, 20 angstrom thick, and you tilt it by 1 millirad, that it's 0.06 degrees, the consequence of this is a parallax of 1 picometer. That means you simply by mistilting your sample by this small amount leads to a projection inaccuracy of your measurements. And of course, all samples are tilted when it comes to such dimensions. So you have to deal with this. And then there is something which is also normally not considered. We are at the forefront of what is technically possible today. That means you are never sure that the lens parameters which you have adjusted by current adjustment, that these parameters are still valid 1 hour after you have started your session. So you have always to be careful to know the lens settings at the time when you take your image. So that's a lot of things to do, and fortunately this can all be cured by doing a multi-parameter fit. In quantum mechanical dimensions, you cannot easily measure a thickness or a tilt angle. It can only be done by a diffraction experiment. And your imaging process is the only quantum mechanically allowed tool to measure these parameters. So it must be a self-controlling thing. So it's essentially a numerical inversion of the imaging process that we are doing. So just assume that we are doing all this, and then we go now to the results. That means I tilt the sample because we have the results presented in this type of scheme. We have here the atom shifts, and here we have the geometrical location. And so we look what the atomic positions are for the cations, and we find there is not much going on there in the interface. But this is completely different for the oxygen. Oxygen is normally very mobile in these systems, and the oxygen is dragged into the interface. The cations stay behind, and the oxygen is moving towards the interface. And this gives a measurable effect, and the effect is very small, but it can be measured. 5 picometers is the shift of the oxygen into this interface. Now we come to the concentrations, because we have done so much effort to measure these intensities quantitatively. Now we convert these intensities into concentrations, into local occupancies, And there we find a disastrous situation. We have the concentrations are disturbed by over 6 atomic layers. That means we have a disturbance between here and here. And now the concentration is given here. Just an example. This should be the pure lanthanum layer. And you see, only 55% lanthanum, and the rest is strontium. Or this should be here with these arrows. This should be a pure strontium layer. It's only 85% strontium, and the rest is lanthanum. So we have a lot of intermixing going on, which nobody could measure in another way than using this technique. And this then can be used in ab initio calculations, and they have been done, but that's not the topic of this talk. 3D atomic shape of nanoclusters. This is another picometer precision work, very briefly sketched. We have a nanocluster, and it takes a little bit more. So we have here the atoms on top and bottom, and we want to find the structure exactly how these atoms are arranged here. For instance, in catalysis, this would be very nice if we could do that. So this is, in my opinion, to the best of my knowledge, the case where we have driven picometer microscopy to the absolute extreme, because we are able to distinguish between atoms at the top and at the bottom surface in a single image, And the sample is magnesium 001, and you see intensity variations. These are now converted into the atomic image of the surfaces, and we will get data mainly for this part of the crystal. So this is the fit between experiment and simulation, and there is no adjustable parameter, and you see the fit is excellent. It's elaborated here in detail, but that's not important here. And we have also tested by image simulation what happens when this is the sample, when we just put an oxygen atom from the top of the sample to the bottom of the sample, and we get a signal here, which is small, but nevertheless, it's larger than the noise. That means these are significant data. We move a magnesium atom to the top, and so on. So we can test this. So all these processes have been tested, and these tell us that we have single atom sensitivity. We go to the results. This is the atomic structure. This was the image. This is the atomic structure up here. And from this we can evaluate, for instance, the atomic shifts. And you see immediately, when you look closely, that this atom has shifted to the right. And it has shifted by about 15 picometers. And you see it directly. Another nice feature of this study is that we found a better fit when we assumed that in these magnesium positions, we have half atoms. So what is half an atom? It took us some weeks to speculate what half an atom is. And then one of my students came, and he went to the old literature, and he found a study where people have studied ultra-pure magnesium oxide surfaces. And they found that even on these very pure surfaces, there's always carbon contamination. And then we did a DFT calculation. This tells us the carbon wants to substitute magnesium atoms. It has half the nuclear charge, and this is where the factor 1/2 comes from. Electron energy loss. Shortly, because the chairman has already signaled that my time is running out, we have seen some results on lanthanum aluminate strontium titanate interfaces. These are images taken in the light of a particular energy loss, which is specific for the atomic element. And we see here the last strontium atom layer. And you see it has a somewhat lower intensity. That means less strontium. And we have here the lanthanum yields image. And we see some intensity there, which corroborates our results, which we have just seen. So these yields studies are done today or since quite some time in the high energy range, and a very recent development is ultra high resolution low loss yields. For this, you add a monochromator to your stem, which monochromizes the electron beam to 10 milli-electron volts. And this allows you to study energy losses very close to the zero loss peak. There is something going on here, down here. We magnify by a factor of 1,000. And here you see a nice peak of the longitudinal optical phonon of hexagonal boron nitride at 173 milli-electron volt comes out. This means that we can do very precise low energy loss spectroscopy, which is interesting for surface science. And now surface scientists are buying this type of spectroscopic microscopes. Last topic, experiments in situ in the electron microscope under direct observation. For this, we do the environmental transmission electron microscope. We have a sample chamber here, reaction gas comes in, sample holder. We have small apertures here and differential pumping here so that the vacuum here is still 10 to the minus 10. And then we can study reactions here. We can also do plastic deformation experiments, just to show you this nice picture here. And then we can study, for instance, a silicon atom cluster on graphene. No time to go into detail. I want to go to the last example here. And this is gold nanoparticles as catalysts under reaction conditions. And gold, the oxidation of carbon monoxide into CO2 has been studied since many years, and people have found out that gold nanoparticles, when they are smaller than about 15 nanometers or so, when they are on a oxygen support, oxide support, they act wonderfully as catalysts in this reaction. And all these studies that have been carried out, also the theoretical calculations, they assumed cubic FCC gold. And you see, you can measure the atomic distances here, and they fit very nicely to FCC gold. But now you put the CO2 atmosphere in your sample chamber. So this was all in vacuum, in the microscope, same microscope. You see the same particle here. And now something very unexpected happens. This gold particle undergoes a structural phase transformation from FCC to hexagonally close packed. And in this, now the reaction takes place, and the adsorption of CO can be studied in this particular structure doing DFT. These are the surface atoms of gold, and it turns out that the CO is arranged in such a way the C binds to the gold and the oxygen is here. This gives very weak contrast. These are the carbon, this is the oxygen, and this fits, in particular, this contrast fits to what you observe at the limit of what you can do. And please understand, these are images taken in an oxygen atmosphere, in a CO atmosphere. So this is giving you the state of the art in this. Just to summarize, we have seen that aberration-corrected optics has changed the landscape in electron microscopy. We have atomic electron microscopy. We have picometer microscopy. We can measure local atomic concentrations, and we can do high-precision yields. But beware of oversimplifications. We are working in quantum physical space when you do atomic electron microscopy. That means we have to invert the imaging process on a computer and, if possible, to combine with ab initio calculations. Every month, new applications are coming up, so I think the future has just begun. One day, aberration correction, I think, will be standard in essentially all microscopes. This is a highly demanding technique, very powerful, and it starts with the investment between 3 and 8 million. Sometimes more. And it requires an experienced specialist, at least in the moment. So my advice to everybody involving this, go to the electron microscope specialist, team up, just solve your questions, specialist collaborating with the other specialists, because I think that's the rule of the day. We have very sophisticated techniques, and it's not easy that somebody just knows all this at a given time. Thank you very much.
Thank you, Knut, for an amazing talk and fantastic examples. We have a few minutes for comments, questions, please.
Thank you.
There's a microphone, so wait a few seconds until the microphone reaches you.
Thank you, Knut, for this wonderful talk and for the wonderful invention of the aberration-corrected microscope. So now we have one here in Jerusalem at the Nano Center as well. And what I'd like to ask, definitely you showed us the challenge of nanoparticle imaging. Now, many nanoparticles have an organic-inorganic system where we're coated by organic monolayers. So part A of my question is how to handle degradation by the beam and beam sample interactions in general. And second, is there a hope to image those monolayers, perhaps?
I think it is in principle, it depends on the details. I think in principle it's possible to image these surface layers. That means you can take a gold particle. We had a lecture on this where you have organic material around that. I think that can be solved. What we cannot easily solve in general is the interaction of the electrons in the beam with this organic coating. Then we immediately have the critical electron doses, which are also important in cryomicroscopy and so on. So, as in many other cases, we do the work with this technique with the samples which are not seriously damaged by the electrons. And the others, we cannot do much with them.
Yes, another question here, and number 2 there. Microphone.
Regarding the last example of gold nanoparticles, how easy or difficult will it be to get similar information, very impressive one, of course, on alloys of gold?
Yeah.
Is it possible to distinguish between the two elements?
Absolutely. I think you can take any type of gold alloy where you have catalytically active centers in addition. There is no problem to solve the Schrödinger equation numerically for a column of atoms where the atom types change. That means people have done calculations where you have maybe 20 atoms of type A, and you have one single atom in that column at some depth, and you can calculate that. Because we are very sensitive in these quantum mechanical calculations, and if these are combined with careful measurements of the intensities, then you can do that. I think that's within reach.
Okay, next question there.
How do you derive the occupancies of atoms in these cases of disorder? Is it by trial and error? Or
No. Okay.
Because you don't have absolute values of the intensities, right?
Right. So the important first ingredient is to know the intensity in absolute values. So you saw the fitting, and there was no fitting, no adjustable parameter. So the first point is to go through all these corrections until you really have reliable intensities, and then you just solve your equations for different compositions. And this allows you then to measure with, say, a single atom precision the number of atoms of element A and the number of atoms of element B.
And something else which is very dear to our chair, do you have images of quasi-symmetry crystals?
Quasi-crystals, because of Danny standing close to me? Actually, we have tried in the old days, before I left this field. I was very sad about that, but I had a young postdoc, and I had to transfer the field to him because otherwise we would have a problem with each other. We did this type of microscopy, but not with these very sophisticated optics. And quasicrystals are very, very delicate because their atom column imaging is not so easy to do. So that's a challenge. I think it could be done. And it was, there were attempts to do this with decagonal phase in particular.
Decagonal is easy.
Yeah, it's easier because you have periodicity. Because it's no longer such a hot topic, we cannot invest time now to go back to this.
Thank you.
Okay, hey, Knut, thank you so much for a wonderful talk.